How does in situ doping differ from post-synthesis doping, and what implications does this have for uniformity, defect creation, and bonding of dopants? What type of hard carbon material was used? What is its source or structure? And how does it interact with the dopants introduced by this method? What specific changes occur in the carbon microstructure, pore distribution, or electronic properties as a result of in situ nitrogen and phosphorus doping? How does this alteration in the structure relate to the observed 63% increase in capacity performance? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? What is meant by capacity performance in this context? Does it refer to reversible capacity, rate performance, energy density, or another electrochemical property? And how exactly was the 63% improvement measured and validated? What were the baseline and final values, and under what test conditions, e.g.? Current density, number of cycles, electrolyte type, were they recorded? What is the mechanism by which sodium ions are adsorbed by defect states? What kinds of defects are introduced during the doping process? Are they vacancies, dislocations, heteroatom sites, or structural irregularities? And how do these defects act as active sites for sodium ion storage? What thermodynamic or kinetic advantages do these sites provide? Do they lower the energy barrier for ion intercalation, enhance adsorption, strength, or improve ionic mobility? What experimental or theoretical analyses were used to study these mechanisms? Were tools like density functional theory, DFT, electrochemical impedance spectroscopy, EIS, cyclic voltammetry, CV, or transmission electron microscopy, TM, employed to examine the interaction between sodium ions and defect sites? How does understanding the mechanism of sodium ion adsorption inform the future design of high-performance carbon materials? What guidelines or principles can researchers follow to engineer defect states that optimize sodium ion storage? How does this work offer a new way for designing sodium-storing carbon materials? What distinguishes this approach from previous attempts? Does it present advantages in terms of synthesis simplicity, scalability, material cost, environmental impact, or performance under practical conditions? What types of applications could benefit from this advancement? Are there implications for sodium-ion batteries in grid storage, electric vehicles, or portable electronics? And what additional research is needed to transition this laboratory result into a commercially viable solution for next-generation energy storage systems?